All right, let's break down one of the most fundamental skills in science, how to tell if the evidence actually supports the hypothesis. This is a skill that can literally make or break your understanding of pretty much any scientific experiment.
We've all been there, right? You're staring at a graph that looks like a bowl of spaghetti, a table of data with way too many numbers, and a question that feels like a riddle, all while that clock is just ticking down. It can feel so overwhelming, but hey, I promise you, it doesn't have to be that way.
So, here's our game plan for today. We're going to start by decoding the data, then we'll define our key players. I'll give you a simple 4-step strategy. We'll point out some common traps to avoid, and then we'll wrap it all up with a winning formula to make sure it all sticks. Okay, so first things first, let's kind of reframe how we think about this. This isn't about memorizing a bunch of random facts. Not at all. It's about learning a seriously powerful skill that can turn all that scientific confusion into absolute clarity. Here's the best way to approach this. Think of yourself as a detective. Seriously. Every question is like a brand new case file that just landed on your desk. And your mission is simple. Examine the clues, that's the data, and figure out if they support the main theory of the case. Now, to be a good detective, you've got to know your key players. And in our investigations, those two key players are the hypothesis and the evidence. So let's put them under the microscope. When you boil it all down, it's really this simple. A hypothesis is just the prediction of what someone thinks will happen. The evidence, well, that's the results of what actually happened. So a hypothesis is just a statement you can test. It's kind of like a detective's hunch, a really specific prediction about what's going to happen. For instance, a scientist might predict, hey, if we turn up the heat, this chemical reaction is going to speed up. That right there, that's the theory we're putting to the test. And the evidence? That's your clue file. It's the raw data, the observations you make, the cold, hard numbers from the experiment. So in our example, the evidence would be the observation that, yep, the reaction was, in fact, faster at higher temperatures. Okay, now that we know our players, it is time for the game plan. Here is your simple but incredibly powerful 4-step strategy to tackle any of these problems. And trust me, it really is this straightforward. Step 1, you're going to read the hypothesis carefully. Pinpoint the exact prediction being made. Step 2, look at the data, the graph or the table, and find the overall trend. Is it going up, down, or staying flat? Step 3, bring them together and compare them. And finally, step 4, you decide. Do they match up or not? So really, the whole thing, the whole shebang, it all comes down to this one crucial question. Does the evidence you see right in front of you agree or disagree with the prediction made in the hypothesis? That's the core question you have to answer. And look, there are only 2 possible outcomes. If the data trend matches what the hypothesis predicted, boom, the hypothesis is supported. Simple as that. If the data contradicts it or shows no effect at all, then the hypothesis is not supported. Now, knowing the strategy is a fantastic start, but if you really want to become an expert, you have to know the common traps to avoid. So let's take a look at the mistakes that can trip up even the sharpest detectives out there. And listen, these mistakes are so easy to make, especially under the pressure of a test. They're almost designed to play on our assumptions and trip us up. But here's the good news. Once you learn to spot them, you'll be able to sidestep them with confidence every single time. So here are the 4 biggest culprits. First, ignoring what the hypothesis is actually predicting. That's like getting the suspect's name wrong. Second, getting sidetracked by irrelevant data. These are the red herrings of the science world. Third, mixing up correlation with causation. Just because 2 things happen together doesn't mean one caused the other. And finally, the big one, using the word prove. Okay, here's a crucial little detail about the language of science. You'll almost never hear a scientist say a single experiment proves a hypothesis. It's just considered too strong of a statement. Instead, the correct terms are supported or not supported. Getting this right is a major key to thinking like a scientist. All right, let's bring it all home with the winning formula. Think of this as your cheat sheet, the entire process boiled down into one simple concept. Let's just boil it all down to this simple formula. A hypothesis predicts. The evidence shows. If there's a match, the hypothesis is supported. If there's a mismatch, it is not supported. That's the entire game in a nutshell. And here are some rapid-fire tips for when you're in the hot seat. First, physically underline the key prediction in the question. Make it stand out. Next, actively hunt for the pattern in the data. Up, down, or constant. And finally, mentally block out any extra information designed to throw you off. Just focus on what really matters.
If you remember just one thing from all this, let it be this. Your job is to match the pattern in the data to the prediction in the hypothesis. It's not about what you think should happen or what you already know. It is only about what the evidence on the page says.
Because ultimately, this isn't just a trick to pass a test. This is the very core of scientific thinking. Taking a claim, scrutinizing the evidence, and drawing a logical conclusion. So my question to you is, what claim are you going to put to the test first with your new detective skills?